Hi, hope you're okay. We will follow now with lecture number 6. Lecture 6 is about phylogenetic analysis, methods of construction of phylogenetic trees that represent relations. So, how can we represent relations? Based on sequences that have a similar function must be descendants from a common ancestor sequence. So, this allows us to understand that if they have a common ancestor and they have mutations that show up over time, and they are there, if we compare the sequences, we can check those differences and weight them and relate the sequences aligned. But we must understand how can we understand evolution, and looking at some characteristics, how can we understand how they evolved? Because having a common ancestor, you need to know that this is related to a divergent evolution, and those sequences or those characteristics are called homologous. So when you say a bird wing, is it homologous of an insect wing, or is it homologous to the human arm? Well, these questions are hard to answer, so you have to look deeply to the structure, like if you were looking at a protein and you have to look into the sequence and to the amino acids. So analyzing, in fact, arms and wings have a common ancestry because they have the same structure, so they had resulted from divergency and they are called homologous. Also, you have both wings that are made to fly, but they have no common ancestry. They result from convergency and they are called analogous. I'm sorry, these words are in Portuguese, but you will learn them as in English: divergency and homologous. So having a common ancestor. If they evolve by convergency, they are called analogous, and they don't have a common ancestor. So there are some concepts that you really need to know. Similarity is just what they resemble. They are not equal. For the name of being equal is identity, and identical will be the same amino acid, the same nucleotide. High identity is usually related to homology. If you have two proteins with more than 25% identity, they can be deduced to be homologous. If you have more than 70% identity between two sequences of nucleotides, either gene or transcripts, you can deduce or infer that they could be homologous. Among the homology that have a common ancestor and they evolve by divergency, you really have two types of homology. The same origin in the same species that a gene acquired a different function, they're called paralogs. If you have different organisms, different species that have the same protein with the same origin that evolved, they're called orthologs. You have already heard these concepts. Phylogeny, it is represented by a tree, and it represents biological relationships. It may be among organisms, among proteins, among genes, and phylogeny can these trees relations that assumes the existence of homology. They're constructed using sequences, molecular sequences. So you have DNA sequences or protein sequences for start, and the basis is multiple alignment. But you really need to have on your background, the evolution of the organisms. You know that man never existed during the time of dinosaurs. And the first organisms were unicellular, then multicellular and colonial, and then evolved to very complex multicellular organisms. At a certain time, they only lived in water, and then after having evolved several plants, then some organisms went to Earth because it was the atmosphere was favorable. In Earth and on oceans and water, there were massive diversity of organisms, and there were also massive extinctions during time. One of the most known extinctions were the dinosaur extinction. There were already mammals, but they were similar to rodents, and only after massive extinction of dinosaurs, the mammals evolved and gave rise to a very, very diverse biodiversity. And you have humans evolving in the last 2 million years. If you want to take a look compared to sunrise like 12,000 million years ago until the origin of humans, it's very, very recent, the origin of human called Homo sapiens. So you have fungi, you have the fish, and you have then some different kinds of fish, real fish, cartilaginous fish like shark. You have the insects. You have at certain points the amphibians, and then the evolution of reptiles. After reptiles, you have the evolution of birds, similarly the mammals, and then you have very recently the plants with flowers and bees, and then finally the evolution of primates where human beings belong. So, and you have a scale of time, geological time, and the origin of Earth is 4.5 thousand million years, and the origin of life closely to 3,000 million years ago, and only human beings from like 2 million years ago. And it's pure fiction when you see dinosaurs with humans. They didn't exist together. They got extincted before the evolution of the mammals, although they existed already. So they have sequences in common. We have sequences in common with bacteria. They are very ancestral. So after a multiple alignment, you can get that multiple alignment in different formats. You start with FASTA format with the sequences using Clustal or any other multiple alignment software. You can get different formats. Clustal, that is ALN, and that is alignment format, or Phylip format. This Phylip format is the input for the software that performs phylogeny analysis. And this multiple alignment format has a particularity because it has the number of sequences, the length of the alignment, and then you have only the names in the beginning, and they're cut with 9 characters, and the sequence starts at 11th character. So you don't use long names to your proteins or genes in analysis when you prepare your FASTA format. Multiple alignment can be then used to have a distance matrix or perform the phylogeny and the relations in a tree. For that, using Mega software, you have to convert the Phylip format to Mega format that has this aspect. You have the sequences all separated but with the length exactly the same, keeping the gaps and all the sequence alignment. At Mega you can get the distance matrix where is represented the distance between those sequences calculated based on models. Most of the models are similar to substitution matrices, and then you can check that between TBP1 and TBP2 there's a distance of 0, so you will have no distance between the two isoforms of these proteins. And then you have distance between humans and mouse and rat and chicken, and the higher level of distance is between the humans and fruit fly. These distances are useful to construct the tree and define the length of the branches in the tree. So, if you use different methods of phylogeny, the phylogenetic methods may be based on characters or may be based on distance. Distant methods, like for example neighbor joining, are based on phonetic theory and is distant based. And then you have Homo sapiens with a representation of a node, it's the common ancestor, and no distance, there's no branch to each human clade TBP1 and TBP2, but then you have different sizes of branches, and here you can check that a chicken, a bird, is closely related to Homo sapiens than other mammals. So this wasn't the best result as expected. So you always have to criticize your results and be careful in analyzing. Human clade is always on the top, and these numbers are related to statistical analysis of each node that represents the common ancestor. And the last one is the root of the tree. In this case, it's the fruit fly that roots this tree. And you really need to pay attention, because in order to increase the analysis among the clade in analysis, you should always introduce a different organism in order to ensure the relations that you are analyzing. And if it messes all up, it shows to you that are not the best sequences to analyze, or you're using wrong parameters to perform the multiple alignment and bad methods to construct the relation tree. You have also methods based on cladistics and character-based, for example, maximum likelihood or maximum parsimony. You can take a look deeply into the methods based on phonetic approach, their clustering approach. So based on the distance matrix that may be resulting from a megafile and the alignment, the multiple alignment performed on Clustal, then you have this distance matrix that helps you to calculate the size of the branches for your tree. So you start with the closest taxa. Taxa may be represented by sequences, by organisms, either nucleotide sequences or protein sequences, or you just name it A, B, C, D, and you will have the lower value in this matrix is the one that shows that those sequences are closely related. And then you calculate the branch. The unweighted pair group method with arithmetic mean is based on arithmetic mean, and you can calculate the distance dividing by 2. So if the distance between these two sequences is 1, it's 0.5 and 0.5 to each of the places. And then you merge the two sequences because they are now having a common ancestor. And then follows the calculation of the branches between each other sequence and this new common ancestor that is located here. And let's find out the other lower value, and the lower value is between these two sequences. It's the value of 2. So these two sequences, if their distance is 2, halfway you have a distance between each of the sequence and their common ancestor is 1 and 1. 1 plus 1 gives rise to 2. And then you follow to calculate once again the matrix between this common ancestor and the other common ancestor, and you have a value of 3. If you sum this 2.5 with 3.5, you have 6, and dividing by 2 arithmetic mean because you have two sequences, then you will get branch between this and this common ancestor to their common ancestor like 1.5. And this was the first type of approach of clustering sequences and constructing a phylogenetic or a relation tree. But as we can see, always the distance between each sequence or each taxa with their common ancestor is always equal. So several other methods were evolved in order to calculate and to have different distance between common ancestor and the taxa that are originated. So neighbor joining was developed based on the UPGMA method, and it performs corrections and allows better results. Character-based methods like maximum likelihood and maximum parsimony are based on characters and mutations, and maximum parsimony is based on or tries to find the minimum number of mutations, because along the evolution there's no big mutations, because big and high number of mutations give rise to organisms that do not evolve. And maximum likelihood is a lot more complex. It's based on the quantitative probability of a mutation event. It's highly more complex and highly demanding for computation. It is also used and also available at Mega software that you will use, but is less often used. Finally, most of the trees you have to validate statistically and the most used method is bootstrapping, although there are also other statistical tests to a phylogeny and to give some statistical significance. Once again, you must not forget that these are only results that are from in silico analysis, and computational analysis may help you to infer about the real relations, but you need really to test and compare to other results and be criticist. Thanks for your attention. I hope you enjoyed, and meet you soon, probably on another subject or in practical classes. Bye for now.